Can you hear me? Okay. This is Błażej Kubiak. My name is Krzysztof Kudryński. And this is a drone. Now it is in the box, but the world consists of two groups of people. People from the first group will immediately take the drone out, start to enjoy flying, while people from the second group will immediately download the API. Now there is absolutely no shame to be part of the first group. I have real friends that would actually do that, and they are nice people. Myself and Błażej, we are proud to represent the elite. After over 3 years of dealing with the drone, we have absolutely no idea how to fly that thing manually. So in this project, the drone will learn to fly, and it will learn that skill based on what it sees. And it will see the world with just a simple monocamera. And the first step in this project will be just a calibration chessboard. You always look at this kind of very well-structured objects to find the distortions in the camera and then correct them so that you can see a nice world. In fact, then you continue your project with detecting chessboard in the image and then tracking a chessboard in the movie. These are the hello words of computer vision. But if you are here to see the hello world application, you might get a little bit disappointed. Although we cannot disagree that finding a chessboard and detecting a chessboard are so interesting projects, so useful in real life with great real-life applications ranging from detection of freaks still playing chess on a chessboard up to detection of people walking on the street with a chessboard. Well, our project is inspired by something completely different. These are the fragments of drone races taken from the web, and you can really feel that speed. It's so amazing. And when you actually realize that these videos, these races were controlled manually, there is one word that is screaming in your head, which is irresponsibility. So let's analyze one case. This is a frame taken by the drone during a race. And well, the task for a user is to apply control a little bit to the left and fly forward. It's so simple. There's a lot of time to do that, but if you are actually starting to worry now, you are doing the right thing, because although there is still a lot of time to react, well, you all know how it's going to end. Oh, I'm sorry. So, while there is so much time to react, which you can see, oh my God, what's going on? Sorry, technical. Well, you can see there is so much time to react. Similarly to other videos which ended in a silly crash, while there were tens of frames begging for salvation. Now, together with Błażej, we decided to put an end to that. As a user, you should only select where you want to fly, and it is the machine that should calculate all the low-level controls to make that happen. And today, we will try together to walk through all the steps that you need to make this happen on the machine. And we'll show you the results on our own project, but you will not see it in the ruins like that or in the forest or parking lots, but instead we'll show you our tests in our modern TomTom office in Łódź. But if you look at it very carefully and at the right perspective, you cannot miss the similarity. We are absolutely sure that this office was meant to be our training ground from the early beginning. Okay, for initial inspiration, let us analyze this simple case again. We all have to agree that we humans are just amazing. Everyone here, immediately and without any effort, is able to spot a nice, safe place worth flying to. Everyone here, immediately and without any effort, is able to apply proper control. Everyone here, immediately and without any effort, is able to spot the collisions and act accordingly. This is already amazing. This is purely amazing about our brain. But what is even more amazing, that during exactly same time, in the exact same moment, with the exactly same brain, we humans are able to plan our next meal or perform deep considerations about life. Well, this is still, that such general intelligence is still beyond the scope of science. And we will not tell today how to teach the drone to cook or understand life, but we will focus on these three particular tasks. And when implemented on the machine, we will clearly see how it outperforms human performance very soon. So these three tasks will be tackled throughout this presentation. Let's start from some basics. You can use whatever equipment you want as long as you can communicate with it from your API. We used Parrot, AirDrone 2 from the shelf, and then we downloaded Java framework, open source framework to communicate with it over Wi-Fi. It's called Yadrone. It's under Apache 2 license. You can download it freely. There's a lot of other stuff. You can use it. And then in this framework, there is thousands of lines of code. And the line that we used, only one, is the move command, where you just specified the tilt, how the drone needs to turn left, right, tilt in Y direction, speed in Z, and speed of rotation. So these four parameters you supply to the move command, and you will derive these parameters by analyzing the video, which from our experience was the most convenient to decode using C++ FFmpeg, and then analyze these images using some Python code, using libraries like OpenCV and NumPy. And then everything was analyzed in the control center, which we planned to write in Java and send the commands to the drone. Now, this is like initial design of the application, but you will see it gradually changing because we will add new elements to that. But having the backbone architecture, let's think about the most important thing, which is the logic of our application. So let's first start with the first level of autonomy, which we need to supply, which is tracking. And because we are fans of human brain, let's think how we humans would do tracking in real-life situations. And for that, let's imagine that we go to the club full of people and we find something very interesting, something that catches our attention, and we really want to track it. For example, a hat. But for a start, imagine something more familiar. You must imagine it really hard. Imagine that instead of a hat, we have a chessboard. Now, this does not happen really often, but if it was the case, we would have our predefined chessboard tracking algorithm to do the tracking for us. However, sometimes it happens that we have to track something else. And it is at this particular moment when this region gains some description. Maybe the description, the distribution of colors inside this image, maybe the shape of the hat itself, maybe the flow of pixels inside our specified region. Well, all of these approaches can be easily tackled by the machine. And the good news is that we don't need to implement it ourselves, because there are libraries like Open Computer Vision library from many languages, Java, Python, C++, with wrappers everywhere. So here you can decide what you use from the API. We checked our solution from MinShift, which is just calculating distribution of colors inside some region, and then scaling this and shifting this region so that the distribution stays the same. In cam shift, very similar, but you also apply rotations. In optical flow, you are just using some mathematical tricks involving Taylor expansion, first order, to analyze the flow of pixels inside the region. So you can just use it. You don't even need to understand too much. And from our perspective, optical flow gave the best results. So let's see it in action a little bit. What you can see here is our graphical user interface. So this is what the drone sees, and this is overlay of some of the controls that it will automatically generate. The arrows on the left and right shows how we need to tilt to omit an obstacle. Then there is an arrow on the bottom which says, well, maybe we need to go higher because there's an obstacle. Now, the most important in this case, these arrows in this first exercise will be 0 because we are now only at the level 1 autonomy, which is just tracking. So we will focus mostly on the red circle in the middle. It is in the middle now, but when we start flying, we will click on this white table on the left, and it will be tracked. And then you will look at the arrow on the bottom, on the top, sorry, which shows what rotation needs to be taken so that we are actually flying towards the object that we are tracking. So let's start flying. You can see that after we fly manually, there is a optical flow tracking the region, and we see the strong desire of the drone to turn left, which, if we press 1 on the keyboard, will in fact turn into action. So we will be floating freely and tracking the region that we are, and we'll be focusing on this region which we are tracking. So this is our autonomy level 1, very simple. When we talk about autonomy level 2, there's not much to add. We will just fly towards that. So this is very simple, as you will see from these examples. However, yes, without a proper collision avoidance, this is not very good to use it in unfriendly environments. So this is how we arrive at level 3 autonomy, which is where the fun begins. Because we want to fly in a 3D environment, omitting obstacles, while we have only a 2-dimensional image. And that is a challenge. So the question that we will ask ourselves again would be how we humans would do it. And probably the first answer that comes into our head is through the pair of our eyes. Let this be a diagram, a simplified diagram of our viewing system. The blue rectangle is where the image is formed, and the line in the middle is its principal axis. And in fact, when we a single pixel in this image shows us very limited information about the object that lies in the world. In fact, it only tells us on which line this object lies in space. We don't know how far it is, unless we have another eye, which, by the way, is quite common. So in this other eye, we find the corresponding pixel, and with very simple mathematics, we find where this object lies in the world. So, is stereo vision an answer? Maybe yes. We could just go and replace our mono camera with a stereo vision system, probably more expensive, probably heavier than the first one. So before we all go out shopping, let's ask ourselves another question. Are we humans hopeless if we only have one eye? Obviously not. Because in fact, when we move, our eyes feed the brain with multiple images of what we see, and it can be mathematically proven that if in between these two images we find at least 7 points in general non-critical configurations, we are able to first derive the movement and find the structure of the object which we are looking at. So up to scale only. So this is a video, this will be a video of my chair. And in each image, the algorithm will find some characteristic points in this video, and frame by frame, it will calculate the corresponding points to the previous points. And then on the right, it will generate the 3D structure while the video is being recorded. You can see here, this approach is known under many names, from structure from motion, multiple view reconstruction, visual slam. And there is OpenCV library where you can do basic reconstruction. There is a lot of open source materials in the web which you can use. And there are a lot of amazing books which you can read and write your own better code. If you do it right, the results are amazing, especially if you move horizontally versus the object which you are tracking, because then every frame gives you a lot of other perspectives on the image, on the object you are looking at. The problem is when you actually move towards this object, because with every frame there is very little additional projective information of the object you are looking at. And in fact, you may project your world, 3D nice world, to be flat. And that is not true. It goes even worse if you just rotate, because then all of the rays meet at the same focal point anyway, so there is absolutely no projective information in successive frames. So this is not very cool, because our very nice approach is at its worst case, because when we are racing in our video with our drone, we are actually moving forward and probably rotating most of the time. So this is the worst case for our nice algorithm. Another simple algorithm might be using just optical flow, which we just discussed. If you notice the door handle and the glass, when we move, the door handle, which is far away, moves much slower than the glass, which is close, and we can use this information to reconstruct a little bit the spatial environment. However, again, here we would need to make sideways moves in order to make that work. So one way to solve our problem would be, while racing, deliberately add sideways motions to our drone. For us, Polish people and our friends in Russia, adding a little bit of slaloming path to our movement would be probably perfectly excused, but we would not win the race that way. So, are we doomed to fail? Absolutely not. And again, we will draw inspiration from the power of the human brain. Because we humans, we do not need two eyes to understand the space around us. We do not need to move around. We can stand still in one place and have absolutely no doubt what's around us. How do we know that? From experience. From thousands, from millions of images fed into our brain, we learned to understand objects, their perspective, their relative sizes, their arrangements, and their shadows. With our lifetime experience of looking at the world, we humans need no tricks to understand the space. And as amazing as it may sound, with the recent advancements of artificial intelligence, we can share this experience with the machine. And today, we will show you that we will be training a deep convolutional neural network to perform this task. And before Błażej will give you some details, if there is anyone here absolutely unfamiliar with the topic, I'm sure not, but generally, in the handcrafted algorithm, you find a set of rules, formulas to actually detect an object, decide something about it. In machine learning, you build a model so that it takes all the input, calculates some combinations and combinations of these pixels to give you output, and to make it a correct output, we flood it with examples. And then from the backwards, you learn how this should optimize the model. But you can read a lot about that. But today, instead, we would show you some amazing experiment. In this experiment, you will be the AI, and I will train you to perform a simple categorization task. In the beginning, as a typical neural network, you have absolutely no idea what you will be learning, and one by one, I will show you images with labels, and your brain will shape itself, will optimize seeing these images and labels, so finally, when I show you just an image, you will know the label without me giving you any additional information. So you will see how this works in action, so let's go. Image number 1, label. Image number 2, label. Image number 3, label. Image number 4, label. Training time is over. Now it's time for a test. Please don't hurry up, you have a lot of time. Now there are 2 allowed answers, yes and no. So please now raise your hands who votes for yes. Okay, okay, thank you. And now who votes for no? Okay, thank you very much. This is 5,035 for yes and 1 for no. Ladies and gentlemen, this is a correct answer. You have successfully detected a sofa. I really appreciate your cooperation. That was very nice. Your votes are very important for us. So, we are the winners. However, there is something disturbing here. There is one guy who was blinded by some less important features also available in this image. Now, this is a threat. If there were more animal lovers in this room, we would miss to deliver the lovely sofa. So seriously now, this is a real concern in AI. Preparing a good, precisely shaped, well-representative data to train is an art. And sometimes you just need thousands of examples, especially for the machine that has no previous experience. It has to learn everything from scratch. And sometimes, as a designer, you have to make a choice if you can afford producing such loads of training data, because maybe you have just one example and you can intuitively create your own algorithm to solve your task. In our case, manually handcrafting an algorithm would be pain. Yes, would be pain. Because what we want to do, we want, having one image, we want the machine to give us the 3D environment, which may be in form of a depth map where black is near and white is far away. And then if we had this, we could just detect the objects which are close to us and try to omit them very easily. So, because it's so difficult manually, we will try to train a deep convolutional neural network to do that. But, as we just said, in order to make that happen, we need a training set, a training examples. In other words, if we want to ask the machine to give us, for every image, this depth map, first, we need to show it 100,000 of examples of this job done right. So how can we do this? How can we prepare this training set? And one way to do this would be to take a ruler and for every pixel in this image, measure the distance from your camera to the object which we are doing, which we see in the image. So we would do this for all of the pixels in the image, and then we'll repeat it for all of the training examples. And our rough approximation says we would need about 300 years to do that. So we decided to choose a different solution. We said before that our structure from motion algorithm is not good because we are just flying forward and rotate. And that's true. But when we collect ground truth, when we want to train the algorithm to understand the space, we can use it because we can create a much different scenario where side motions will exist. So we will, in fact, do some side motions first, and then we will move very precisely from 0 to 4 meters to some object, a pillar in this case, hence the name deep pillar learning. So as you can see, we are moving, and we see the depth map of the nice depth map of our image, more or less. The problem is with the scale, because I told that structure from motion gives only depth map up to the scale, but we know our scenario was perfectly planned. We were moving from 0 to 4 meters from a pillar, so we can just create a histogram in time, locate our pillar in this histogram, and then normalize it to lie between 0 and 4 meters, and then reapply this normalization back to the photos. And we will have a perfectly created training set to teach our algorithm to do it without structure from motion. So generally, I must say we are very shy, but we are in love with our solution. But to tell you the truth, it's quite complicated. There's a lot of work to do, and there are much simpler ways to achieve that. Błażej will now tell you about this and about our architecture, and later I will show you in action.
Hello. Okay, thank you, Krzysztof, for great introduction. So, as Krzysztof said, it's great to migrate things from scratch. However, many times it's much wiser to use existing solution. So we used one existing solution and it was a deep neural network trained for depth estimation. And what was really nice, not only the network structure, but also the model was available to download from GitHub. It was available in 2 formats, in TensorFlow and also in matconv.net, but TensorFlow is a more popular one, so we use that one. And there was also Python script that we could read and check how to use the network, how to load the model, how to feed with our custom data. So we did first test. We taken picture from our drone camera, and we wanted to test it with this deep neural network that we downloaded from the web. So we were a bit scary because the model size was like 200 megabytes. It was loading like 5 minutes, and the estimation on CPU took like 30 seconds. So for real-time solution, it wasn't acceptable. But fortunately, we found out that we have very nice, powerful machine with 2 GTX Titan X graphical cards in our TomTom office, and we use that one, and we get around 100 milliseconds on inference, so it was quite nice. 10 frames per second was acceptable for our solution. So we could just use that solution and go forward with that. But we are guys that want to know always what is under the hood. So we explored the solution, how it works, and I will explain it in some details now. So the solution is deep, fully convolutional neural network with upscaling layers fine-tuned from residual network 15. Yeah, it sounds strange, so I will split it and try to explain it one by one. So let's start with simple neural network. Probably everyone has seen such picture. It is a simple, fully connected neural network where every neuron is connected to every neuron in previous layer. And all these connections are weighted, so there are weights that are changed during the training process. And during training process, we are feeding with some data, putting some output, and we are trying to change this weight with algorithm called backpropagation to make the proper output at the end. So why can we just use such simple well-known architecture? So let's imagine that we want to feed such network with the image 100 by 100 pixels. In terms of number of weights, you would end up with almost billions weights. So imagine that you have to update a billion weights in every training iteration. That network would never converge to some stable solution. That's why we are moving to convolutional neural networks. To explain how convolutional neural networks works, we need to explain a few concepts. First is simple operation that have on the left-hand side we have the picture, on the right we have kernel or filter, in other words, where there are some numbers, and in the output we have just sum of multiplication between corresponding pixels. Let's see how it works in some example. So the kernel has some negative and on the left-hand side and positive values on the right-hand side. So as we see, this filter exposes edges in that image, and this is the thing that the neural network is doing with convolution. So the kernels are trained to expose some features, to show nice properties that can be used for classification. Next thing is max pooling. It's very silly operation that is used for downsampling image, and it just take the maximum value pixel for each 4 pixels in the input and put it in the output. And it is quite silly, but if you think that that in previous layer in convolution we expose nice features, we can expect that most important value will be in maximum value pixels. So it's quite excused though to use such simple operation. Last operation is also quite simple and quite silly. It's used for upscaling, and for every pixel we just put this pixel in output in left upper corner. And maybe you may think that these all zeros are not important in the training, and in fact are not important, but we always use these unpooling layers with convolutions. If they are involved, they are interleaved, and thanks to that we have some interpolation of these values and nice output at the end. Last thing is important is activation function that is used. It's rectified linear unit, and it is basically linear function that is saturated to 0 for negative values. So let's see how typical convolutional layer looks like. So we have the image in the input. We have kernels, so or filters. So there are separate filters for each channel. We sum together, perform activation function, and we have our feature map. So there are these features that are exposed by our kernels. If you want to have multiple feature maps, we are adding multiple set of kernels, and we have multiple features. If we want to compare it with fully connected layer, we see that with the limited number of weights, like 27 for 3-channel image, we have a feature map. On the other hand, if we want to have multiple feature maps, like 100, we'll have like 3,000 weights. But in fully connected layer for the image, we would have 300 million weights. So the number is quite huge, and it shows the difference. So the convolutional layer with limited number of weights are producing many features that can be used later on in classification part. But in fully connected layers are good for classification because they aggregate features with big number of weights and produces small output, which is basically output of our network. Which is also important, fully connected layer is not local. So because every neuron is connected to every neuron in previous layer, there can be some network may think that there is some relation between grass and the rubbish bin here, and there is no locality. But because convolutional layer works on filters that works locally, maybe smaller or bigger filters, but works really locally. So they show some local properties in the image. So, this is a typical picture of deep convolutional neural network, where its first part is feature extraction. As I said, it is consists of max pooling and convolution, so it produces features. And there is classification part that consists of a few fully connected layers. These days, it's quite popular to remove this classification part at all and exchange it with another convolutions and poolings, and we have just one pixel at the end. This is for reduction of weights, number of weights, so to have the model of the network really small. Yes, and at the end, the pixel is just the output of our network and set if it's true or false, or saying the label for classification task. Could we use that network for our case, for dev estimation? Maybe yes, but for whole image, we would have just one output, so it wouldn't work because we want to have full resolution depth map for each frame. That's why we are using upscaling layers that I was mentioned before. So after a few upscaling layers and convolutions, we have fully resolution depth map at the end. This kind of networks are quite big and it's difficult to train them. So we are using quite nice techniques, which is called Phi Tuning. So we are using the network that was trained for completely different tasks, like classifying dogs and cats. We can remove some part from the end of the network or change the network. And the guys from the paper I mentioned use the reasonable network 15, trained for classification. They remove some classification layers at the end, added upscaling layers, and trained this network for dev estimation. And the results are very nice. So you see the grant of images. So the data set is the middle. On the left-hand side, you see RGB image, and on the right, you see depth prediction. And they are maybe a bit smooth, not so sharp, but for our task, it's just perfect. Yes, now Krzysztof will continue.
Okay. So let's come back for a while to our initial design, which was already a little bit complicated because of various components written in different languages, but now it goes even worse because not only do we need to port everything to a Linux machine with CUDA support, but we also need to run our Python model, which loads 200 megabytes every time we want to do the inference, which would kill us if we want to do it in real time. Obviously, it's solvable. There are a lot of people who can make this work as a perfect unity, but for those who cannot, the world brings microservices. From 2017, when you have a presentation without microservices being mentioned, it's considered crap, so we couldn't risk, we had to say. But in fact, we are just decomposing our architecture into client-server components, which saved a lot of trouble to us. And now we have just our core, which is a Python application, which is served from the C++ FFmpeg service decoded images. Then it asks CUDA server for the response, a depth map from every image. And then the control server, you can manually control the drone or ask for autonomy level, which is calculated then and served to the control client, which controls directly the drone. So, having all of the puzzles solved, let's finally show how it works in action. And we are very happy to be able to show you this demonstration video, because during recording we had a fire. If you don't know what a fire is a set of failures that every self-respecting developer should experience during the day of delivery. And we really had that. In the demonstration, you will not see it perfectly because we are using most secure delivery platform proven to be PowerPoint. Now, seriously, all the pieces work together perfectly, but we had some lagging communications. So frankly speaking, this will be the best video out of probably a dozen. But let's have fun watching it. So you see our drone flying. In the top, in the bottom left, you can see its imagination of the environment. So when the blue regions comes up, we can see the controls automatically applied to the drone to omit that. So we can see that the object which is tracked is the window on the opposite side of the room, and the drone by itself flies towards that space without any human intervention. You can see that it is flying really fast, so we can already race. There is no problem to win. Now, in order to prove how repetitive is our process, we will show you the same video again. But now let's just relax and see how it works. So, as discussed in the description of the task, the user only selects where they want to fly, and the machine calculates all the low-level control from its understanding of the environment, which it gained through learning from experience of the depths which are understandable by human. And it's coding the future. So generally, that concludes what we wanted to show to you today. But in our final words, if maybe we offended anyone while we tried to be funny, please accept the following rectifications. First of all, dogs are more lovely than sofas. Second, not all chess players are freaks. Actually, when you play chess with your old, nice, traditional chessboard, it can be a nice game. And finally, irresponsibility is fun. Two rules to remember when you actually do that is to watch out at the lamps in your office. And second, if you actually manage to record a video of your drone, for example, crashing into the workspace of your boss, never show it in public. Thank you very much.